there would have been handouts here. And let me show you what they look like. Here we go. So, and let me get a little closer. That's the Thermochemistry chapter that we're going to do today. It's my chapter 6. And let me see, your chapter. You're chapter 5. In your textbook, it'll be chapter 5. We'll cover the same material. And then there's the review document, right? And here are the work problems that go with it. They are in Brightspace. So let's talk about thermochemistry. And let me share the PowerPoints. Okay, thermochemistry. You guys have probably gotten a snoot full of chemistry already, so you have an idea of what chemistry is. Thermochemistry is that branch of chemistry that deals with the transfer of heat during a chemical reaction. And most chemical reactions will either generate heat, give heat off, or will absorb heat during the reaction. Very few of them are neutral. Let's see. I don't know if this is going to be worth the effort, but I'm going to try it. Here we go. All right. Yeah, it's working. Okay. All right. So we need to talk about energy first. I can remember even in grade school, the definition of energy they gave was the capacity to do work. But they kind of left the part out about producing heat. So energy can take the form of, it can either do work, and we have to define what that is, and I'll do that in just a second, or it can produce heat. And we have a general intuition about what heat is. But first, we need to understand that energy, the energy that the universe started with, whenever that was, is the same energy it has now. In other words, energy cannot be created, it cannot be destroyed, it can only be transformed from one form into another. And actually, since Einstein's theory of, I think it was special relativity, he showed that you could equate matter with energy also. So that covers pretty much everything in the universe. This also, we'll talk about this law of conservation of energy in conjunction with some other information. And that'll come under the heading of thermodynamics, which is a broader subject area. We're going to laser focus on just the transfer of energy as heat in this chapter. But that's what the first law of thermodynamics looks like. It's delta E, right? And you know what delta means? Any change, a change in energy. And if we say the change in energy of the universe, that is everything, everywhere, at all times, is equal to 0, which means that the amount of energy you got 10 minutes ago is the same energy you got now. It may not be in the same form, but it's the same energy, same amount of energy. Okay. Energy can take two forms. One is potential, and the other is kinetic. Potential energy is just what it says. It is the potential to do something. It's stored energy is another way of saying it. Whereas kinetic energy is exhibited by motion. Anything that's moving, any mass that's moving has kinetic energy. And that's pretty much one side, and everything else is potential. Now, it can be, potential energy can be in the form of position. And what we mean by that is usually, actually always, positional potential energy is due to the position of an object, a mass, in a gravitational field. That is, it has to be close to a large body. And if you're standing on the surface of that body like this, and you move to this position, something's holding you up there. We don't know what, and it really doesn't matter. Then you have added energy in order to get there. So the further you are away from the body is a store of potential energy relative to that body. In our case, it would be Earth. Okay? And how do you get the energy back? You just take out your supports, right? And you'll go back to the surface. Now, that's not a useful return of energy because you get all that energy back, and then when you hit the Earth, that energy is transformed into some other type of energy, which will break bones, damage internal organs, various things. But all the energy you had and you put in here, you get it all back. Other types of potential energy. Compositional. Compositional potential energy is dependent on sometimes the state of the matter. What state is it in? Liquid, solid, gas, or its relative position to some other body that has some factor. I'm trying to make this broad. Some factor that allows you to store energy. Okay, example, electrostatic. If you have a charge here, a positive charge, and you have a negative charge here, then they're attracting one another. Right? Okay. So to get them apart, you've got to input energy to get them apart. Well, as long as there's a measurable attraction between the two, then if you let them go, they will slam back together and you'll get that energy back. That's electrostatic attraction. Repulsion could work the same way, right? If they're both positive charges, then the closer you push together, then you're storing energy between those two particles. It's kind of like magnetic potential energy, right? Magnetic. So if you have a magnet here with a north and a south pole, and you have a magnet here with a north and a south pole, they're going to be attracted to one another. And to get them apart, you have to input energy to pull them apart. And if you let them go, they slam back together. Other types of compositional. Elastic. Elastic potential energy. Think rubber bands, right? This rubber band. If I stretch it, I'm putting energy into it because I'm expending energy to get it to this position. All right. And all I have to do to get the energy back is to let go. And the energy comes back. That's elastic potential energy. Now, there are lots of different types of elastic potential energy. This is just one example. Chemical energy, the energy that's stored in chemical bonds. And how do we measure that? Well, if you have a compound here and something happens to it to make separate elements or compounds, doesn't matter, then in order to get there, you had to break bonds. Okay? So usually when you break bonds, you put energy in. But when they settle down to this position, maybe you get energy back. So really the way we test chemical potential energy is what's the energy state here? What's the energy state here? And you just subtract the two. What's the difference? And that will give you your change in energy. And you can tell at that point, if E2 is larger than E1, then you released some energy in the process. And vice versa. If it's opposite, then you put energy in and stored it. So you can store energy in bonds or you can get energy back. I think nitroglycerin. You can make nitroglycerin. All you need is glycerin, which is an organic compound, and nitric acid, concentrated nitric acid, and then a little bit of sulfuric acid in there also makes the process go faster, and you get your nitroglycerin quicker. Well, you've stored energy in it, in that compound. How do you get it back? You just take the nitroglycerin and drop some of it on the floor, and it will explode. So you're getting energy back from the chemical bonds that were formed when you made it. Nuclear. So you can have nuclear potential energy. Nuclear potential energy is, well, there are branches of chemistry that deal with it, but nuclear potential energy comes from the nucleus of the atom. And there are two types. You can either get at that energy by fission or by fusion. Okay. In fission, you take an unstable, usually very heavy element, like uranium-235, okay? And you hit it with neutrons. If you hit it with a neutron, that makes it so unstable that it splits, right? And it splits into products. I can't remember what they are, but say you get something here and you get something here. The way you know the energy, and it gives off energy. Okay, so how do you rationalize the release of energy? Well, now you need, I was going to say Isaac Newton. That's a little too early. Albert Einstein. Einstein said that the energy that you get out of this reaction is equal to the mass times the speed of light, equals mc squared. So the mass, in this case, the mass is the difference between these two. So if this is mass before, or initial mass, and these two together make a final mass, then the difference between these two is that value. And that disappearance of mass is what is converted into energy. So that's nuclear energy. Similarly, if you do fusion, and a popular way to do fusion is with tritium and deuterium, and you make helium. with some neutrons. I think one neutron will do it. That's 5, 5. Yeah, that'll do it. So the same thing happens here. The mass of these two together compared to the mass of these have less mass than these two. And that difference in mass is what is converted into energy. So that's nuclear potential energy. Now, I did all that talking about other types of energy, and I saved our current interest to last: thermal potential energy. Thermal potential energy is measured by a difference in temperature. If a change in temperature occurs, then heat has either been added or extracted from something. That's potential energy, that thermal potential energy. And we use thermal potential energy every day, all day, 24/7, 365. Any power plant, modern power plant these days, uses thermal potential energy, usually in the form of steam. Use some source of heat, chemical reaction or a nuclear reaction, to store energy in pressurized steam, and that steam is driven through turbines that drives a generator and produces electricity. So we've got various forms of energy cascading through the system to ultimately produce electricity. And thermal energy is an intermediate step in that. All right. So how do we get a handle on kinetic energy? With a formula. Kinetic energy is equal to 1/2 mass times velocity squared. So anything that's moving and has mass will have kinetic energy. And it doesn't matter the size of the particle or the size of the mass, this formula works on anything. Except when you get subatomic particles where quantum mechanics kicks in, or very large like black holes when relativity kicks in. But anything in between there is fair game. So remember the fundamental units that are applied in the SI system. Mass is kilograms, right? Velocity is meters per second, but we're going to square it. Right? So what are the units of energy in this case? The units of energy in this case are kilogram, meter squared, per second squared. One of those is equal to 1 joule. Joule is the standard, a derived unit, not a fundamental unit, but a derived unit of energy that's equal to this. It's equal to other things too, and I'll point those out as we go along. But you can measure kinetic energy. It's easier if the object is large enough that you can put it on a scale and it's not moving too fast. As long as you can measure both the mass and the speed, you can calculate the kinetic energy. Or you can measure the kinetic energy by energy transformation, right? You could shoot a cannonball at some predetermined object at a given temperature, and then when the cannonball hits that stuff and stops, all of its kinetic energy is converted into something, and usually that takes the form of heat. So when it converts into heat in the capture zone, the temperature should increase, and you can measure that. As far as chemistry is concerned, all molecules have kinetic energy in any substance at any temperature except absolute zero. Absolute zero says that there is no motion whatsoever, no kinetic energy. Right? That'll never happen. Think about it. How do you get to lower temperatures? You usually take advantage of the fact that anything that's hot will transfer heat to anything that's colder than that. So you have to have a cold sink, a heat sink, to take the heat out of that other object to make it colder, right? So how are you going to take enough heat out of something to get it to zero? There's nothing colder than zero. So you cannot reach zero in a substantial amount of mass. Now, that some researchers have claimed that they have reached 0 K with individual atoms and molecules. They somehow or other, they know they can calculate and they can fix the trajectory of an atom or molecule moving at them. They hit it with a laser with just enough energy to stop it. And for that instant, there's no motion. It is at 0 K. But for all practical purposes, we're never going to reach it on a large scale, a measurable scale. Okay, there's your formula. Now, let's talk about the transfer of energy. We've got these two balls, A and B, and A's got a certain amount of positional potential energy. And B is sitting there at the same time A is. It's lower energy, right? Because it's closer to the surface of the Earth. So what happens when you release A? I don't know what's holding it there, but if we remove the restraints and let it fall, what's it going to do? Well, it's going to hit B. And if the collision is perfectly elastic, that is, all the energy of motion that A obtains when it falls is transferred to B, then A will stop and B will move until it rolls up the other side and stops over here somewhere, right? So theoretically, we would expect that B to take all that energy, leave A here, and transfer B up to here at the same level. But that won't happen. And the reason it won't happen is, let's see. The reason it won't happen is that some of the potential energy is lost during the collision and while the balls are rolling, right? Due to friction. And that's called frictional heating. So we haven't created energy, we haven't destroyed it, we've just transformed it, right? So B only rises to that first plateau. And it rises there because some of the energy was lost by the collision itself, right? When those things smacked each other, they made the molecules move and heated them up, lost some energy. And rolling on the surface, they lost some energy by friction with the ground, right? But we still have all the energy accounted for, either in the form of potential energy, positional potential energy, or heat. Okay. Now let's pause for a minute and try to clarify the relationship of temperature and heat. They are related, but temperature is an intensive property. We can measure temperature of anything, any substance. And the temperature says that if the substance is this big and it's 20 degrees Celsius, and you have that same substance, but you have more of it at the same temperature, it doesn't matter how much you have. When you say it's 20 degrees Celsius, you don't care how much there is. You're saying that the temperature in that substance, however much it is 20 degrees. That's an intensive property. Doesn't matter how much the substance is. The temperature, though, is a way of measuring the random motion of the molecules. In other words, the more energetic the molecules, the more faster they're moving, the higher the temperature. So temperature is a measure of average kinetic energy of all the molecules in the substance. The temperature doesn't tell us what the kinetic energy is. It's just a way of getting at the average kinetic energy. We're saying that the kinetic energy, if it increases in the substance, the temperature will also increase. Okay, now what is heat? If we know temperature is this, then what is heat? Heat is, we don't know that heat is even there unless we measure the temperature. But that doesn't tell us how much heat is there. What we need is to measure the transfer of that heat from one object to the next. So in order to do that, we need two substances in contact with different temperatures. And if this one has a higher temperature than that one, heat will transfer this way. Okay? And we give heat a special symbol. It's called Q. Just a little Q that represents heat. Heat always transfers between a higher temperature to a lower temperature, which means that now we can get a handle on the heat that's transferred based on the temperature. But we need more information than that, because temperature is an intensive property, and maybe we have a little bit of some substance here, but at some other time we have more. They might be at the same temperature, but we can rationalize, we can reason that there's more heat at that temperature if you have more of the substance. Right? So we need a way to get at that, quantify the amount of heat. Okay, we're going to do that in a minute. But first, I want to go back to the original definition of energy. Energy is the capacity to do work or create energy, create heat. Do work or release heat. Okay, so what is work? Well, if you take a physics class, you will learn that work is this. Work is only measurable when you have a force acting through a distance. Right? So if I stand here and push on this board, I'm applying a force, but the board's not moving. So I'm not doing any work. But I am expending energy. Right? I have to expend energy to push on that wall. Right? So where's that energy going? If I put energy into that board, where does it go? It's not moving. It's all being transferred and converted into heat. But if I push on something and it goes a distance, then the force that I apply, newtons, times the distance in meters, gives me a value for work. 1 Newton through 1 meter distance is equal to 1 joule. Okay, so now we're starting to build a repertory of conversion factors. Right, 1 joule equals 1 Newton meter. 1 Newton meter equals a joule, but it also equals a kilogram meter squared per second squared. Okay. So we've got several conversion factors that we can rely on, depending on whether we need to cancel values in a calculation. All right, so that's the definition of work: force acting through a distance. All right. Now I'm going to introduce another concept. It's the difference between a state function and a path function. Right? A state function is any process that happens and it doesn't matter how it got there. Right? We start from here, we end up here. We could go like this, or we could go like this, or we could go straight. The function that's applied to that, if it's a state function, it doesn't care how we got there. Okay? Whereas a path function does matter. The values, the units of measure, and the values that come out of a path function depend on the path that you take. So if, say we're in Charleston, and we're going to Beckley. And now we can go on the turnpike. And the turnpike does twist a little bit, but say it's relatively straight. Right? So how much energy is expended to get there? Right? In the form of gasoline, say. Prior to the turnpike, actually, even before the turnpike was a two-lane road, you had to go back roads. You might have to go down to Prince, say. Find your way down to Prince, cross the river there, come back up to the other side, and make your way to Beckley. Or you could go from Charleston to Montgomery, and then up through the hollers there to Oak Hill, and then around to Beckley. If you take those alternate paths, then the path function is going to be a different value if you go that way. Okay? As it turns out, work, W, work, and heat are both path functions. That is, it depends. You apply a force and you go through this distance is a different amount of work than if you go through this distance with the same amount of force. Right? That stands to reason. And the amount of heat that's required to get there, say through your automobile engine, right, takes more to get there this way than it does to get there that way. Okay, those are path functions. The amount of potential energy that you have stored in your car and yourself by going from here to here, right? The potential energy is a state function. The amount of energy that you were able to store in your automobile by going from there to there is, it doesn't matter how you got there. The only thing that matters is the distance you moved and the force that's applied, right? So potential energy is a state function. Okay, there's just definitions for you right there in black and white. Okay. We're still trying to get a handle on how to measure transformations of energy. And in order to do that, we need some devices. One of those devices is, what is the system? What are you actually talking about when you're discussing an energy transformation or chemical reaction or whatever the case may be? So we have something called a system. And the system is anything you want it to be that will help you solve the problem. Sometimes it's evident, right? Right from the start, what your system is. Sometimes you might have to think about it a minute and say, all right, if I do it this way, I can't solve the problem. If I do it this way, I can solve the problem. So here's your system. Everything else is surroundings. Okay? So we've defined what our system is. We've defined everything else as surroundings. And there's our little animation. Sometimes, in fact, very often, it's useful to limit the surroundings. Instead of the surroundings being the rest of the universe, which is kind of hard to get a handle on, we say the surroundings are maybe some box that we created and we put our system in it. Then everything that's not in the system is surroundings. In order to do this, we've got to make that boundary impenetrable. Matter can't cross it, energy can't cross it. That's called an isolated system surroundings. Okay, now the system, we can also describe the system, this boundary, in terms of either matter crossing it or energy crossing it. If energy and matter both can cross the boundary, then we have an open system, right? So this is energy, and this is matter. I'm just going to say mass. That means open. Sometimes it's useful to let that happen. And sometimes in nature, when you define your system, you find that that does happen. Matter and energy do cross the boundaries. Living systems are often like that, only they're slightly different. An open boundary in a living system is usually controlled. So it lets mass in sometimes and it lets energy in sometimes another way. Right? So there are various applications in the natural world. Okay, what if we restrict that boundary to only energy? In that case, we're talking about a closed system. In other words, it doesn't let matter come in or out, but it will allow energy to transfer. This is much more common for our purposes. And then the isolated system, where you don't let anything cross the boundary. That sometimes is useful, right? And when we talk about calorimetry, I'll have to define that term later. We use this. The system then is completely isolated. Okay, those are the three types of boundaries you can have in a system surrounding settings. You could even do that with the surroundings, but it kind of defeats the purpose. If anything can cross that boundary, then you haven't isolated, you haven't restricted the possibilities. Okay, so when a chemical reaction occurs, in terms of the heat that flows either into or out of the system, if energy flows into the system, we say that's an endothermic reaction. Right? So if energy flows, let's say heat. Let's restrict our discussion now to heat. If heat flows in, that's endothermic. And remember, anytime we're describing a process, it's always in terms of the system. What does the system see? The system sees energy coming in, heat coming in. So we're adding to the system. So in terms of the system, the sign on that value, any value that we give it, will be positive. And we say it's endothermic because it's into. Heat is going into the system. Okay? If heat goes out, then Q will be negative. And this is exothermic. Exo means out of, like exit the building. Okay? In this case, the surroundings acquire some heat at the expense of the system. In this case, the system acquires some heat at the expense of surroundings. Now, if this is all isolated, right? If we're isolated, then the energy that's lost by the system, the heat that's lost by the system has to show up in the surroundings. In other words, it's a zero-sum game. So let's look at the let's look at some examples and see if we can make sense of them in terms of what we just discussed. Freezing of water, is that an endothermic or exothermic process? Well, first of all, you've got to define your system. So what is your system? Well, let's say we're using an ice cube tray. Right? So you've got various depressions in this ice cube tray, and you put water in it, right? So that's liquid water, right? So that would be our system, the water in the tray, right? So now, what are the surroundings? Well, the cold environment, right, in the freezer is the surroundings. So which way is the heat going to flow if water freezes? If it converts to a solid. How do you make something a solid without changing its chemical properties, without changing its identity? You have to extract heat from it, right? You have to remove heat from liquid to make it solid, right? So the heat transfers from the water into the cold air in your freezer, right? So the heat transfer is this way. Negative, which means it's exothermic. Okay? Let's see, is somebody chatting? I'm looking for it, but I don't see it. Oh, okay. Oh, yes, there is supposed to be a test today, but it's on Brightspace. So you can take it anytime, turn it in by midnight tonight. Okay. Maybe I need to leave that. I don't want to make it big. Come on. There we go. Okay. So let us proceed. Yep. It's not behaving. There we go. All right. In this case, we've got several scenarios. We're going to classify each one as exothermic or endothermic. Notice that whether it's exothermic or endothermic depends on what we're calling the system. So if you change the system, swap places with the surroundings, that changes the process. It changes an exothermic to an endothermic if you change places with the system, swap it with the surroundings. So in this case, in this set, we're saying that the system is that underlined part of the sentence. Your hand gets cold when you touch ice. Your hand is the system, and it's getting cold. So which way is the energy moving? It's moving out of your hand, right? Which makes it exothermic. Ice gets warmer when you touch it. So now if we define it in terms of the ice that we touch and not in terms of the hand, then from the ice's perspective, it is gaining heat. It's endothermic. water boils in a kettle, right? So the heat is being supplied by the stove. The stove is the surroundings. The water in the kettle is the system, and it's endothermic. We're putting heat into it. Water vapor condenses on a cold pipe. Water vapor is the system in this case. So if water vapor condenses, it goes from a gas to a liquid. What does it have to do? It has to lose energy. It has to lose heat, which means it's exothermic. Okay? Ice melts. So if ice goes from a solid to a liquid, it's gaining energy. It's endothermic. All right. So for any of these problems where you're trying to decide is it endothermic or exothermic, you have to define the system, you have to define the surroundings, and then decide which way is the heat moving. And that will tell you if it's an endothermic or exothermic process. How about methane burning in a Bunsen burner? Right? So we got our Bunsen burner, right? And we got a flame here, right? Like that. And we got a tube here, goes to the gas cock. So methane is burning. Methane is in here. Oops. CH4, right? Plus oxygen. So what is the system? The system is not the burner. The system is the methane oxygen mixture. Okay? And it is giving off heat. We can feel it, right? The heat's being released by this reaction to the surroundings, to the room, which is the direction is exothermic. So the sign on anything we gave to this process would be negative. How about water drops sitting on your skin after swimming and they evaporate? All right, what's the system? Well, you could call it your skin, but I tend to call it the water. The water is the thing that is doing the transforming. It's changing from liquid to gas. And in order to do that, it has to absorb energy from your skin. Your skin is the surroundings. So that energy is being transferred into the water, makes it an endothermic process. Okay. Let's see. Do I want to stop on this one? Yes. Hydrogen gas and oxygen gas react to form water. Hydrogen gas and oxygen gas react to form water. Okay? It doesn't say what form the water is in. So this is a gas we know. This is gas we know. This could be liquid or gas. We don't know yet. Just for argument's sake, let's balance this equation. So we need 2 waters to make 2 oxygens and then 4 hydrogens. Okay, so now it's balanced. All right. If it reacts violently, they're implying that it gives off energy. It's exothermic. Right? It releases heat. Right? Releasing heat from the mixture means it's exothermic. Okay? Now let's look at it in terms of energy balance. If we got energy out over here, where was it before? It was in here. So this is higher energy, right? Initial, higher energy than that one. Because now at lower energy, we get some of this out. And sometimes when I write chemical equations, it's convenient to say, okay, if this is an exothermic reaction, then there's going to be heat on this side as a product. If it's an endothermic reaction, and it wouldn't be this equation, but if it were, then we would have heat coming in this side, stored in the products over here. All right. So in this case, the water that forms over here is lower in energy than the reactants. All right, we mentioned thermodynamics before. We're not going to spend a lot of time on it here, just to say that thermodynamics studies the interconversions of energy. And look at the word thermo meaning heat, dynamics meaning motion, as opposed to statics, right? Dynamics is moving, statics is sitting still. So it studies the movement of heat in any process. It doesn't have to be chemical. So enough said about that. We'll talk about it again in subsequent chapter. Now there's the concept of try to get at what is the total energy of your system and how do we quantify it? Well, you could have potential energy stored in the system, in the chemical bonds or in heat, or you could have, and you often do have, at the same time, kinetic energy. The particles are moving, right? So you've got both potential and kinetic energy in there. But there's another way to get at it. And we have to see a change in energy in order to quantify it, right? We can't look at it in absolute terms because we don't have access to the absolute. In other words, we don't have access to absolute zero. So we look at it as a change in energy. So if the system undergoes a change in energy, it can only do it in one of two different ways. It can change the amount of heat it has by a change in temperature, or we can measure work either being done by the system on its surroundings or by the surroundings on the system. And these terms are all in joules, right? Right? They're all apples. Apples, apples, apples. Joules, joules, joules. All right, let's see if internal energy concept is useful. When we're talking about a thermodynamic quantity like energy, the value or any quantities that we measure or calculate have three components. One is the number, the magnitude of whatever change has occurred. Right? There'll be a number associated with it. There'll also be units of measure, should be joules. Most of what we're going to do is in terms of joules, but there are other energy units that you could use. And last but not least is the sign. The sign tells you which way the energy is moving, right? Is it moving, is the change going into the system or out of the system, right? So I mentioned this earlier, so I'm not going to stop here for very long. Endothermic processes into the system, Q is positive. Out of the system, Q is negative. But the same concept is useful for work also. Right? If the system is doing work on its surroundings, then the value of W, in this case, the value of W, the work being done on the surroundings, is leaving the system, so it has to be negative. But if the surroundings are doing work on the system, the value will be positive. Now you may be asking yourself, how? I can understand how heat moves, right? But how do you do work on a system, or how does the system do work on its surroundings? There has to be motion, and there has to be a force. The easiest way to think of it is in terms of gases, right? If you have a gas in a cylinder with a piston, right? You have your gas in here, and that's your system, that trapped gas. If the piston moves up, the gas is doing work on its surroundings. If the piston moves down, then the surroundings are doing work on the gas. And there's always a force involved. The gas is applying a force through a distance, or the surroundings applying a force through a distance. Now, usually that's measured in terms of pressure, but we'll talk about that again in just a second. Oh, I got a video. Now, this is Professor Dave. He's going to talk about some things that we haven't covered yet. So just kind of let them flow over you, keep them in the back of your mind, and we'll define them and talk about them after the video.
Hey guys, it's Professor Dave. Let's talk about thermochemistry.
He knows a lot about the science stuff, Professor Dave explains.
Thermochemistry is the branch of thermodynamics that deals with the heat absorbed or produced by a chemical reaction. A reaction can either be exothermic, one that releases energy, or endothermic, one that absorbs energy. This change in energy is represented by delta H, or the change in enthalpy for the reaction. For our purposes, we can think of the change in enthalpy as being the change in energy for the reaction, or the energy stored in all the bonds of the products minus the energy stored in all the bonds of the reactants. If there is more energy in the products, delta H will be positive, meaning the additional energy had to be provided, making it an endothermic reaction. If there is less energy in the products, then that additional energy was released, making it an exothermic reaction. Energy, which is the capacity to do work, can have many forms, like mechanical, electrical, chemical, heat, and so forth. And besides quantum mechanical exceptions, energy is conserved. That means it can change forms, like heat energy that evolves when the chemical energy in a broken bond is released, but it won't be created or destroyed. Heat, represented by the letter Q, is a trickier thing to define, but a good way to put it is that heat is the energy that flows between a system and its surroundings due to a difference in temperature. Heat will always flow spontaneously from an area of high temperature to an area of low temperature. For a system, Q will be positive if heat is being absorbed by the system, and it will be negative if heat is being released by the system. When temperature and pressure are constant, Q equals delta H, the change in enthalpy. When we discuss thermochemistry, we will discuss energies in terms of joules or kilojoules. Another common unit used by chemists is the calorie, which is equal to 4.184 joules. 1 calorie is the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. This is not to be confused with the food calorie, which is calorie with a capital C. This is actually equal to a kilocalorie, or 1,000 calories, also abbreviated as kcal. A thermochemical equation reports the change in enthalpy for a given reaction in stoichiometric terms. Here, the delta H listed is specific to the molar quantities given by the balanced equation. So if the number of moles of each substance as given were to react, the change in enthalpy would be as listed. To find the enthalpy change for a specific amount of material, just do some stoichiometry. If twice as many moles of material as are listed were to react, then the enthalpy change would also be twice as much as listed. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me, ProfessorDaveExplains@gmail.com.
Okay, I cut Professor Dave off short because we're going to look at those types of calculations later. But he mentioned this term enthalpy has the same units of measure, joules, as the Q. And he also mentioned calories. When I was a student, we did all our calculations in calories. The problem with calorie is if you don't know that conversion from calories to joules, then calories stand out there by themselves and they're useless for anything else. But if you know joules, then you can do interconversions with other units of measure in the SI system. So that's why we're sticking with joules now. Okay, so we're going to talk about enthalpy in just a minute. But right now, I want to go back to that gas that's confined in the cylinder and talk about how we get at the value of work for a gas that's either compressed or expanded. In this example, it looks to me like here, this is before, this is after. So what we've done is we've allowed the gas to expand under a constant pressure. And it's moved through a distance, and pressure represents a force. And the change in volume has occurred. So in that case, the gas has done work on its surroundings. And so the value of W is going to be negative. All right, and these are all the terms are defined here. Force, distance moved, which is the same as delta H, the distance of the force moving. A is the area of the cylinder, delta V is the change in volume, and P is the force per unit area. Right? That's what pressure means. Okay, so there's the work. Our definition for work is force times distance. All right. Pressure is force per unit area. All right, so we got that. But we want to define work in terms of something we can measure in this example of an expanding gas. So if we look at work equal to force through a distance, then if we solve this for force, PA, then we can substitute this in there. Okay? Now, change in volume is the other thing that we know. Change in volume equals the distance traveled, delta H, in this case, little h, is our D, times area. Right? That's the volume of a cylinder. So you're looking at the change in volume is actually a cylinder, and the height times the area is the volume of that cylinder. So that's what we're saying here. Right? Now, if we solve for D over A, we can substitute that in here. Okay, and that's what we're going to do in the next animation. All right, so if we put this one in here and this one in here, you get this formula right here. And notice that area is in the numerator over here and then the denominator over here, so it cancels. So work is pressure times change in volume. Now, in many cases in the real world, pressure will not be constant. Pressure will change. But I'm going to show you in a minute that constant pressure is desirable for other exchange of units and meaning of values. Particularly, how is this one related to that one? Okay. But there's a fly in the ointment, as they say. As delta V, we've gone from a small volume to a large volume. So the change in volume is positive. This value, let's see, W equals pressure times change in volume. This value is positive under that scenario. And we're letting the pressure be constant. So it's positive, whatever that happens to be. So work in this case calculates out as positive value, correct? Right? Positive times positive is positive. But our system, by our convention, our system is doing work on the surroundings, which means work is being lost by the system to the surroundings. So the signs don't match. So what we have to do is fudge. So here's the way we fudge. We say, in order to make it work out right, put a negative sign right there. W equals negative pressure times a change in volume. And that will make the convention work. Now, work comes out as a negative. Okay? Now, sometimes, notice, let's go over here. Work equals a negative P delta V. If we say, like we were working with gases earlier, if we say pressure is in atmospheres, right, and volume is in liters, right, then the units of measure here for that work will be liter atmospheres. But that's not joules, obviously. We can't associate it with any other energy-related activity because it's in the wrong units. So we need a conversion factor. And that's what that one of these is equal to 101.3 joules. There's your conversion factor. And if you look at your review document, you'll find in the back the this conversion factor is in the useful information. Right? So use it a lot and you'll memorize it automatically, or refer to the useful information for that value if you need it. So which of the following here performs more work? A gas expanding against a pressure of 2 atmospheres from 1 liter to 4 liters. Right? So in the A possibility, what do we got? What's pressure? Pressure is 2 atmospheres, right? So work equals negative 2 atmospheres times a change in volume. So how do we measure changes? It's final minus initial. So the final is 4 liters minus 1 liter, right? So that's 3 times 2 is minus 6 liter atmospheres. Okay? There it is. Now, I'm not going to draw the second one on the board because we go through the same steps to get to the next one. And if we do the calculations for B, we find out that it is also 3 atmospheres moving 2 liters is minus 6 liter atmospheres. So A and B have done the same amount of work on the surroundings. And notice the value is negative. So that indicates that the work is being done on the surroundings by allowing the gas to expand. All right. This one will take a little bit of mental dexterity. And drawing a picture really helps. Okay. Determine the sign of delta E for each of the following with the listed conditions. So for A, the process is endothermic and performs work. So this is endothermic. And performs work. And what we're saying there is it performs work on its surroundings. So it's endothermic and work on surroundings. So here's our process. For the first one, notice those two bars on either side, right? What does that mean? That means absolute value. So the absolute value of work in the first scenario is greater than the absolute value of heat. So what we need to do is say, all right, here's E equals work plus change in energy equals work plus heat. Okay? So the first one, we say we've got work. Let's do it this way. Let's spread it out some. There's work and there's heat. Okay. All right. So for this process, if work, the value, not the sign, but the absolute value of work exceeds heat. So this one is greater than that one. What will delta E be? Right. If it's endothermic, that means heat is moving into, and we're doing work on the surroundings, which means this is positive. So if this value, absolute value, is greater than this one, then it favors the positive, right? And that's positive. The other way around. Excuse me. It's still positive, negative. But now if it's back the other direction, if the value of heat, the absolute value of heat is greater than work, right, then the negative is favored. And the change in internal energy is negative. Okay, how about B? For B, we have an exothermic process and work on system. So work is being done on the system. Okay, so work now, yeah. Wait a minute. No, I did that wrong. I'm sorry. I did that wrong. If it's endothermic, that's positive. Work on the surroundings is negative. Okay. Now, if this one is greater than, then you have negative. And if it's that one's greater than, you have positive. Okay. Now we turn it around. For an exothermic, then this value, Q, will be negative, and W will be positive. Okay. Now, what happens if work is greater than heat? Now it's positive, delta E. And the other way around is negative. Okay? There we go. Negative, positive, positive, negative. All right. Now, what do we mean by enthalpy? It's important to recognize that heat, Q, is not the same as enthalpy, a change in enthalpy. They're like second cousins. And sometimes they come together for family reunion. But they represent completely different values. Q is the amount of heat that's transferred to and from a system. And it's one of the two means that we can change internal energy during this process, this thermodynamic process. All right, so that's Q. Enthalpy is, it's better to think of enthalpy as potential rather than actual. It's like internal energy, but there's more to it than that. There are situations in which if you measure the Q of a transfer, then that value will be equal to enthalpy. And Professor Dave mentioned that. We're going to talk about it in just a second. But the equation that defines enthalpy is it's a change in internal energy, but you also have to consider these other factors. Change in pressure times volume. Right? So if there's no change in volume, or there's no change in pressure, that means there's zero, the change is zero, then these two values become equal, internal energy and enthalpy. But that doesn't help us much. We want to find out under what circumstances can we take the measurement of heat transfer, Q, and say that is equal to enthalpy. Why? For the very simple reason that these both are state functions. These two. It doesn't matter how you get there. So if we know the enthalpy value, then we can do a lot more with it without having to worry about the in-betweens. Whereas Q and work are path functions. So under what circumstances, if any, will this value be equal to Q? Right? That's what we're getting at now. And we start from this equation. Oh, good. Zach's back. So what is the equivalent of delta E? Well, the only other formula that we've come up with for delta E is this one. Right? So if we substitute that in here, that's what we get. Q plus W plus delta pressure times volume. We're not there yet. If this process occurs at constant pressure, in other words, we pull that pressure out so that it doesn't change. We only let the volume change. Pressure is constant. Then we get this equation. See how we pulled the pressure term outside the delta. Now pressure is constant. All right. Let's carry it one step further. Work is equal to negative P delta V. So enthalpy then can be Q. Well, I didn't write it up here, so can be Q. And then what stands for work? Well, negative P delta V is work. And then P delta V here is positive. There it's negative. They cancel each other out. So with this equation manipulation, we see that under conditions of constant pressure, enthalpy equals Q. So that's why many experiments that chemists do, or physicists for that matter, for thermodynamic information, they will maintain the pressure constant during the process. That guarantees that when they measure the Q, then they can equate Q with enthalpy. All right. the moral of the story is that it's easy to get enthalpy and heat confused. But if we use prudent equivalents under these conditions, then they can both be related and useful. Okay, let's see. We got an example here. We're going to work a problem. Let's say you are studying a process that takes your system from a condition of pressure 1, volume 1, temperature 1 to pressure 2, volume 2, temperature 2. Okay? Let's see. I'm not sure if I have this worked out. I think I do have it worked out. There are many paths that you can take to get there between those two thermodynamic states of pressure, volume, and temperature. And along those paths, the values of Q and W will differ because they are path functions. However, no matter how you got there, the delta H will be the same. Whatever the path you take, delta H will be the same. It is a state function. Now, Professor Dave mentioned this equation also. You can take that for the reaction, and if you know the values of the enthalpies of the products and subtract the enthalpies of the reactants, you can theoretically determine the delta H for the reaction. And that's only under those circumstances where pressure is constant. If pressure 1 equals pressure 2 in this case, then delta H will be the same as Q. But if we let the pressure vary, then those two values will not be the same. All right. So we've come to this point so far. Oops. Yeah. Now let's look at it in practical terms. What good is thermochemistry? What can we do with it? Well, in this case, in this example, we've got propane right here, and we're going to burn it in the atmosphere, so it's going to combine with oxygen, and that oxygen is plentiful, it's excess. So we're going to consume all of the propane that we're given, and it produces carbon dioxide and water with this stoichiometry. 1 mole of propane with 5 moles of oxygen will produce 3 moles of carbon dioxide and 4 moles of water. And if we let that happen, what we will see is that that reaction will evolve. See this negative sign right here? That negative sign says it's exothermic. It will give off 2,221 kilojoules for every mole of propane, right? So that kilojoules, very often when you are looking up information for an equation, like you have a reaction you're interested in, and you're looking in a reference manual for that particular equation, and if it has thermodynamic data available, it will give you the delta H for that reaction. But very often it will give it to you in terms of joules or kilojoules, and that's it. It won't have a denominator, moles of propane, for instance. What that means is that it's that many kilojoules for this reaction as balanced. So in this case, it is per 1 mole of propane, but it's also per 5 moles of oxygen, or per 3 moles of carbon dioxide, or per 4 moles of water in this reaction. Now, how do we use that? Right? This particular example is saying that this equation, propane plus oxygen, yields carbon dioxide plus water. Okay? And it's saying that our enthalpy for that reaction is minus 2221 kilojoules. Okay. What it's asking for is calculate the delta H, the enthalpy for this reaction, if you only have 5 grams of propane and excess oxygen. Okay? So, how do you do that? Well, the equation is written in terms of moles of reactants and products. So, mass doesn't help us. We need to know how many moles is that. So, dimensional analysis tells us that we're going to go 5 grams, and we need a value for molar mass for that compound to go right here. So we need 3 times 12.01 for carbon and 8 times 1.01 for hydrogen. I need a new marker. I have one in my pocket. Yeah. Got one right here. Need my calculator. So 3 times 12.01 is 36.03 plus 8.08 for the hydrogens. So that's 44.11 grams per mole. So we need the grams on the bottom. So remember, all conversion factors are equal to 1. Just flip it. 4, 4, 1, 1. Okay. How many moles of propane are there? I get minus, let's see, 0.1134. 0.1134 moles of propane. Okay? Since this is in terms of that balanced equation, and this is per mole of propane, there we have a conversion factor, right? We have moles here. What we need over here is moles on the bottom, which we already have, kilojoules on the top, minus 2221. So now I just multiply that value times that value. And I get 2.5, let's see, 2 significant figures is how we started. So 2.5 times 10 to the second kilojoules. Okay? Now, depending on what units we need, you can change that to joules, or you can change it to standard notation, whatever the case may be. All right. So this, they kept 3 significant figures. I only kept, oh, I should have. I'm sorry. There's 3 there, 3 there. So this should be 2.52 times 10 squared, or 252 kilojoules. Negative. Right? That means it's exothermic, and this is the amount of energy you will get from burning that as chemical potential. And it's measurable as heat, obviously. Okay, so how do we do that? How do we get at heat, right? It's taken an hour and 3/4 to get to this point. We talked about it in the beginning, getting at heat transfers by noticing the change in temperature. So that's where calorimetry comes in. Metry refers to measurement, and calor refers to heat. So we're going to measure the heat. All right. Okay. So this is the science of measuring heat. Before I get to specific heat capacity, let's define heat capacity. What is heat capacity? If you have something here, a mass of something, and it's at a certain temperature, then it will have a given amount of heat contained in it. We don't know how much that is. We only know, and we can only get at the amount of heat by noticing the transfer to something that's colder. But it does have a heat capacity. The amount of heat that's contained in there, and it's given the letter big C. And the units of measure here are joules per gram. No, I'm sorry. It's just joules, heat capacity. No. Excuse me. This is heat capacity. It's an extensive property. That is, the heat capacity will be different if we have more of this mass or less of the mass. And heat capacity units are joules per degree C, which means that for some value here, for every change in degree C, you get a change in some amount of heat. Okay? And if you have more of it, then for every degree change, you get a larger change in heat. But that's not very useful in most cases. In some cases, it's unavoidable. But what's better is to convert this into an intensive property. So an intensive property is that specific heat that's on that slide, right? The specific heat says, and it's an S. The specific heat is the amount of heat it takes to raise the substance 1 degree C for every gram of the substance. Right? So now, having this gram in here in the denominator, it takes away the size factor. Now it's for every gram this happens, and it doesn't matter how much of it there is. That is much more useful for our purposes. A close cousin of this one is the molar heat capacity. And I'm not sure what the unit is. It might be this one is the specific heat capacity, and this one would be, let me just write molar. It's similar to, it's the amount of heat per degree C per mole of substance. Sometimes that is more useful. Okay. So, if two reactants in a solution at the same temperature, right? You got two reactants, same temperature, put them together, and they react. If the combined solution gets warmer, This is an indication that the reaction is exothermic. And if it gets cooler, that's an indication that the reaction is endothermic, because it's drawing energy from its surroundings. All right, there's more to this story. And Professor Dave's going to talk about it. And he will probably introduce topics that we haven't talked about yet, but don't panic. We'll cover them eventually. Take it away, Dave.
Hey, it's Professor Dave. Let's talk about calorimetry.
He knows a lot about the science stuff. Professor Dave explains.
Different substances absorb heat at different rates due to various structural factors. The heat capacity of a substance is the amount of energy required to raise the temperature of that sample by 1 degree Celsius. A variation of this that is more useful for calculations is the specific heat of a substance, which is the energy required to raise 1 gram of a substance by 1 degree Celsius. Heat, temperature, and heat capacity are all related by the following equations. The amount of heat exchanged in a reaction is equal to the heat capacity of the substance times the change in temperature for that substance. Or, more practically, the heat exchanged is equal to the specific heat of the substance times the grams of the substance present times the change in temperature. We can use this information to learn about heat transfer using a process called calorimetry. For those of you in an introductory chemistry course, you'll probably do some variation of a coffee cup calorimeter experiment. Let's look at how those work. A coffee cup is a pretty good insulator. That's why we use it for coffee, so that the heat doesn't escape so quickly and the coffee stays hot for longer. This makes it possible to take pretty reasonable data about the temperature change in a cup of water when we add a hot piece of metal. We can measure the temperature change in the water and use that information to calculate the specific heat of the metal. So, let's say you heat up a metal by placing it in boiling water at a known temperature until it is just as hot as the water. Then, with tongs, you place it in a coffee cup containing a known volume of room temperature water with a thermometer. The water in the cup will heat up slightly as the heat from the metal flows into the water, and we can record the resulting temperature change. From there, we just do some math. We use the specific heat equation and plug in the data for the water. The temperature change is what you recorded. The mass of water in grams is equal to the number of milliliters of water. And the specific heat of water is a known value. This allows us to calculate the heat absorbed by the water. Well, the heat absorbed by the water was the heat released by the metal. So we can take that same quantity of heat and plug it into a new equation for the metal. That value goes there. We weighed the metal beforehand, and this time the temperature change of the metal is from the boiling water to the final temperature in the coffee cup. So you can solve for the specific heat of the metal. This is useful for identifying unknown metals if you are given a few different specific heats and asked to decipher which metal you are given. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me, ProfessorDaveExplains@gmail.com.
Okay. Professor Dave described using the specific, not the specific, the heat capacity in this type of formula and the specific heat capacity in this one. If you look at the units of measure, do some dimensional analysis. This is going to be degrees C. This is going to be joules per degree C. They cancel, leaves us with joules. So that works. This value is going to be joules per degree C, grams. This is going to be in grams. This is going to be in degrees C. So these cancel, and that leaves us with joules, right? So I'm satisfied that the equation at least is consistent with the units of measure. He also mentioned a coffee cup calorimeter. The coffee cup calorimeter is this device that you see in the slide. And it's composed of actually 2 styrofoam coffee cups. And we use 2 of them to ensure the isolation of that system. So this is the case where our system itself, the whole system, is isolated from the surroundings. We don't want energy to cross the barrier or matter to cross the barrier. So everything that happens in that coffee cup stays in the coffee cup. All right, we're going to need a thermometer, right, to measure the temperature change. We need something in here. Sometimes we have water, like Professor Dave described. If you want to determine the specific heat of an object, then you can use just plain water and do those calculations and find out the specific heat of that particular object. Or we can put 2 solutions together and they react. And they either generate heat or they absorb heat. And that happens inside the coffee cup as well. When we do this in the lab, we're going to eliminate the stir, this green thing. The reason for that is I made some of those to work, and you do need to stir the material inside the coffee cup because the temperature you measure needs to be an equilibrated temperature for everything inside the coffee cup. But the material I used for my stirs, under certain circumstances, corrodes. So if we're careful, we can use this thermometer and use that thermometer to stir things around inside. And I'll show you when it comes time to build one of those. Okay. I said that's an isolated system. Heat can't cross the boundary. Matter can't cross the boundary. Okay. So I said it in those terms that what happens in Vegas stays in Vegas, right? Everything that happens in the coffee cup stays in the coffee cup. What that means is all the heat transformations that occur inside that coffee cup, whether they're one part of the reaction gets colder or hotter and the other part gets colder, the total of everything that happens inside that coffee cup must be 0. Because we cannot create energy, we cannot destroy energy. So whatever we do inside that coffee cup has to be equal to 0, right? So if we have the water, for instance, changes temperature, and that shows us that a heat transfer is taking place in the water. And then say we have an object, say a chunk of iron that we put in there at a temperature, whatever happens to it, these 2 values must add to 0. And I think this is actually a more intuitive way and a mathematically consistent way to calculate anything related to heat transfer in a calorimeter than the way that Professor Dave did it. The way he did it was the way that I was taught as a student. I didn't like it then. I don't like it now. I like this method better. Everything that happens in Vegas stays in Vegas, must add to 0. Now, The one thing that we haven't done yet is incorporated any heat change that can be attributed to the calorimeter itself. Right? The calorimeter is not a neutral player. Right? That thermometer has a heat capacity. It can absorb some energy or give up some energy. If we had the stirrer in there, it would do the same. The walls of the cup, that material, styrofoam, it's a good insulator, but it can still absorb heat or give up heat. Right? So we have to determine what is that in our calculation. Now, we're going to do some calculations in a minute, and we're going to assume that that's zero. Right? We recognize that it's not zero, but for the purposes of demonstrating this process, this procedure, we're going to let that one go for now. Okay. All right, so we'll either use this formula or that formula. This formula is useful for the calorimeter. Oops. Pardon me. There we go. I didn't have my silencer turned on. Okay. So if we use this formula and we happen to know the specific heat of the object or the substance, then all we need to know in addition is the mass. But for our calorimeter, we've got a bunch of different things in there, like the cup, the thermometer. They each have different specific heats. So it's more efficient to determine what is the calorimeter constant for that device that you have constructed. And it's unique. Every time you construct a new one, it has a different value. So when we do that lab, I will show you, in fact, in the method, there's a procedure for determining this value. Then we can go ahead with the reaction or whatever the procedures call for. All right, so there's the specific heat capacity. We need to know the mass. We need to know the change in temperature. Remember, delta is always final condition minus initial condition. And that's extremely important for calorimetry because the sign matters. In other words, if this is a positive and this is a negative, or if this is a positive and that's a negative, they need to be equal so that they can cancel and equal zero. So getting those in the right order is absolutely essential. Final minus initial. And what you'll have is this series of Q's, and it can be any number, whatever is required to solve the problem. I rarely have to go past 3. I have gone to 4 heat values in doing these calculations. All right, so let's do some intuition testing here. Let's say we have a 100-gram sample of water at 90 degrees. 90 degrees C. And we put that 100 grams together with 100 grams of water at 10 degrees C. What will be the final temperature? Well, this is an easy one. They're both water, so they both have the same heat capacity. So we can, that comes out of the calculation as a given. So if we have the same amount of each one, this one's at 90 and that one's at 10, where is the equilibrated final temperature going to be? Somewhere in the middle, yes. In fact, since they're equal amounts for each one, their Q values are going to meet in such a way that they're exactly equal. So that means the temperature has to be the same and the difference in temperature has to be the same. So where would we meet between these two? Well, 90 plus 90 is 100, divided by 2 is 50. So they're going to meet in the middle at 50 degrees. Okay, that one was fairly easy, but we're trying to develop some intuition here. All right, now we have something different. We've still got water, but now we have 100 grams at 90 degrees, right? And 500 grams at 10 degrees. So, are these going to meet in the middle? No, they won't, because you've got more at this temperature. So it can absorb all of that heat, or a large portion of that heat, and it will raise its temperature a little bit, and this one will decrease a lot because it's only a fifth of the mass. So the temperature should be somewhere between 50 and 10 degrees, right? And we can calculate that value. Let's see. Why don't we do that? Let's just do that calculation, all right? So the total is going to be 0. 0 equals Q of the hot plus Q of the cold. All right? So what is that going to be equal to now? Well, Q has to be S times mass times delta T. And this is the mass of the hot. The specific heat capacity is going to be the same, right? We just don't know it yet. I'll tell you in a second. So this will be the same for both of them because they're both water. The temperature change is going to be different. So that's the same. This is different, cold. And delta T. This is going to be delta T hot. This is going to be delta T cold. Okay. So now, what is that S value? Well, one of those slides, let me see, during Professor Dave's talk, it showed that value. It's a different value than the one I use. And it's a different value than you'll find in useful information at the end of your review document. But it's this value is the one I'm going to use. 4.184 joules per gram degree C. Okay? What's the mass of the hot? 100 grams. Okay? What's the change in temperature? Well, it's the final temperature minus the initial temperature. Do we know the final temperature? No, we know it's between 10 and 50, but we don't know what it is. So that's your unknown. The final temperature is unknown. The initial temperature for the hot is 90 degrees. Okay, now we're going to add the cold, 4.184 with the same units of measure. Only now it's 500 grams. And it has the final temperature is exactly the same as the cold, because once they put together, they move toward each other and equilibrate at some temperature. So both of these are the same temperature, but the initial temperature is 10 degrees. Okay, now we have an equation in one unknown right here, that final temperature. We just need to do some calculations. All right, so 4.184, this is 418.4 joules per degree C, because we cancel the grams. Okay, and this one is actually 5 times that value. Uh, 2,092 joules per degree C. Okay. Now what do we do? Well, we need a little algebra, of course. So this value times that value is equal to 418 0.4 times T sub F minus 418.4 times 90, which is 37,656. And what would that be? Well, let's see. When we got this one, we're multiplying this times temperature. So this is actually joules. Okay. So on this side, we have 2092 times T sub F minus 10 times that, 20920 joules. Okay. Now we need to combine and get our unknown on one side of the equation. So we'll take this one and this one, right? They're both positive values. Add them together and put them on the left-hand side. All right, so we have 418.4 and 209, no, excuse me. Yes, 2092 plus. So I'm going to take these two, which are positive values now, and they'll be negative on the other side. So I just change the sign, and now we have minus 2510 T sub F equals, now I combine these negatives. All right, so let's see, I want to do that one. No, I want to do this. Let me just punch it in. 20920, enter, and 37656. And this will be a negative 58576 joules. Okay. Now what do we do? Well, we divide both sides by minus 2510, and that gets rid of the negative sign and leaves us with 2510. Yes. And that's 23 degrees C. So the final temperature should be 23 degrees Celsius. Okay? I know it looks like a lot of work, and it is. And it helps if you've had algebra and you can solve for unknowns. And that's the same type of procedure we use with every calculation. All right. Okay, I need to get a move on here. All right. This problem is one in which we have not water and water, we have water at one temperature and an iron ball at a different temperature. In fact, we have 50 grams of water at 10 degrees C and 50 grams of iron at 90 degrees. But now, when we use this equation, we've got two different values for the specific heat. We got a specific heat for water and a specific heat for iron. And notice that the iron is almost 1/10 of water, which means that the temperature of this iron changes by 1/10 of as much for every degree. Right? what's the final temperature? We would go through that same, we'd set it up like this. 0 equals Q of the iron ball plus Q of the water. And we would do those calculations in each one. And in this case, we do have, no, what's the final temperature? That's, again, our unknown is the final temperature. So we go through those, jump through those same hoops with different specific heats. And the temperature now is 18 degrees. Why? Because the iron doesn't have as much heat in it. The specific heat, lower specific heat, means that for a given temperature, the object has less heat in it than for a higher specific heat. In fact, the specific heat for water is very high. That's why water is so good for our planet. Right? It moderates our temperature because it can absorb a lot of heat without very much change in temperature. And that's why our bodies are very consistent. We've got so much water. We're often described as water bags. But the water absorbs a lot of heat for just a little bit of a change in temperature. And that's a good thing. Okay, now we're going to take what we know about enthalpy. Delta H. Delta H is a state function. I said that before, I'll say it again. What that means is, all we need to know is the beginning conditions and the ending conditions. What happens in between doesn't matter. So what we're saying is that in terms of the state function, when we're talking about Hess's law, that means that if we have an equation here, oh, I don't know, CB, say it's a double replacement reaction. If it has an enthalpy associated with it, but we don't want to perform that reaction to find out the enthalpy yet. Maybe the reactants are very expensive and we want to look at it ahead of time and get some ideas how much we can afford to buy. Or if we suspect that these reactants will be very violent, exothermic, right? We don't want to put a lot of them together and explode. So we want a way to get at this value, which will tell us if it's very exothermic. One of the ways to do that using Hess's law is we have different reactions here. And we have a delta H for each one. Right? And I don't know what those be. There'll be some values, some reaction. What Hess's law says is that since enthalpy is a state function, we can combine these individual reactions because the path doesn't matter. We just need to manipulate them, flip them, multiply them by a constant value, whatever the case may be, to make these add up to that equation. And if we do that, then whatever changes we've made to this because of what we did over here, add that together, and that will be equal to this. So we can calculate delta H if we know some intermediate equations that add up to our target. Okay. That's Hess's law. Oh, Professor Day is going to describe it. So he'll probably repeat a bunch of the stuff I said, but maybe say it a little bit differently and hopefully make an impact.
Professor Dave here. I want to tell you about Hess's law.
He knows a lot about the science stuff. Professor Dave explains.
Thermochemical equations can be manipulated to give important data about chemical reactions. We can use them to predict exactly how much energy will be absorbed or released by a reaction, which is very important because we don't want any unexpected explosions. There are two ways we can use tabulated thermochemical data to calculate the delta H of any reaction. The first way requires that we manipulate thermochemical equations in specific ways. So let's be aware of some rules. First, if a reaction has a particular delta H, the reverse of the reaction will have the opposite delta H, or the same number with reversed sign. Second, if molar quantities in the equation are multiplied by a coefficient, so is the delta H. So if you double all the substances, double the delta H. These are things we can do to thermochemical data to be able to add equations together to result in a reaction we are curious about. Here's what I mean. Let's say we want to know about the change in enthalpy associated with a reaction, like this one. But it is difficult to measure experimentally. We can take other reactions with known enthalpy changes and rearrange them to align with our equation and get the data we want. The first reaction provided has carbon graphite on the left, which is where we want it. But the equation we want has 2 moles of graphite, so let's double this one. We get 2 moles of everything instead of 1, and we double the delta H. Next, this other one has CO on the right, where we want it, and in the right amount. So all we need to do is add these equations together. The O2 and CO2 will cancel because they are present in the same amounts on both sides, and we are left with the substances in our original equation. Since we added the equations, we also add the delta H's to get the delta H for our equation. This kind of manipulation is allowed by Hess's law. We can manipulate the coefficients of a reaction or reverse its direction in any way necessary as long as we change the delta H associated with it in the appropriate way. Then we add or subtract the equations as necessary to give us precisely the equation in question. The delta H you get by doing the arithmetic will be the delta H for the reaction. Another way to calculate an unknown delta H is to use standard enthalpies of formation. This is denoted by the following symbol, and it represents the enthalpy associated with forming 1 mole of a substance from its respective elements in their standard and most stable state. Most stable state means the most common allotrope, or physical form of an element. So carbon graphite instead of diamond, diatomic oxygen instead of ozone, and so forth. Standard state just refers to standard temperature and pressure, which is room temperature and atmospheric pressure at sea level. That's what is meant by the degree symbol. We can calculate the change in enthalpy for a reaction by adding up the standard heats of formation of the products and then subtracting the sum of the standard heats of formation of the reactants. The heats of formation can be found in your textbook or online, and you just plug them in, multiplying each value by the coefficients in the balanced equation. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me, ProfessorDaveExplains@gmail.com.
Okay, So Professor Dave introduced both Hess's law and the use of the standard heats of formation. We're going to get to it. This example here is nitrogen plus oxygen yields nitrogen dioxide, and it has a enthalpy of 68 kilojoules for that balanced equation. So what we're going to do is we're going to compare that value with the value we get by adding these other two equations together in the proper form. So nitrogen plus oxygen in the first one gives you nitrogen monoxide with an enthalpy of 180 kilojoules. And the second one is 2 nitrogen monoxides plus oxygen yields 2 nitrogen dioxides with an enthalpy of minus 112 kilojoules. Right? So what you do is you have these equations that are available and they're enthalpies. And what you do is you look at what do you need from the equations, right? You need NO2 on the right. Okay, this equation has NO2 on the right. That's good. This one needs nitrogen and oxygen on the left. That one has nitrogen and oxygen on the left. Now, what they both have is not just the compounds or elements we need, but they also have these other things. Nitrogen monoxide. Fortunately, nitrogen monoxide on this side is the same molar amount as the nitrogen monoxide on that side. So reactants, products cancel. And that's the first condition. You have to be able to add up the reactions to get you your target reaction. So anything you do to them, manipulate them, flip them, multiply them by a constant value, anything you do must yield the target equation when you sum them together. Otherwise, you can't add the enthalpies together. And there we have the final equation, which says that using this method, Hess's law, we get 68 kilojoules as we expected for that reaction. This diagram simply shows you the energy transformations. The one on the left is the two-step reaction where we used Hess's law. And this one on the left is the endothermic reaction, and the one on the right is the exothermic, and when we add them together, we get this overall change, endothermic change of delta H. And if we do them in one step and measure the value, then we get this value, which is exactly the same as the other. Okay. Professor Dave has described the rules. Actually, rule number one is whatever you do, the individual equations must add together to the target equation. And the way you get there is if you have to reverse one of those equations, you change the sign on the enthalpy for that equation. Then, if you have to change the number of the coefficient for any one of the components in the secondary equation, you've got to change all of them the same. The ratio must be constant. Once you've got a balanced equation, then if you double one of them, you've got to double the other. Reactants, products, whatever the case may be. But if you do that, then that same constant value, the multiplier, must be multiplied by the enthalpy for that equation. And once you've got everything satisfied, once you know that you can add them together and get your target equation, then you can add the enthalpies for the overall. All right. Here's an example. I'm not going to go into a lot of detail except to say, notice that this equation has fractionals, fractional coefficients, right? We prefer whole numbers when we can get them, but fractionals work, especially if you consider the equation as in molar terms, right? If you think of it in terms of molecules, then it doesn't make a lot of sense, right? 3/2 of a hydrogen molecule, just can't wrap your brain around that. But if you have a whole mole of them, yeah, you can have 3/2 of a mole of hydrogen. So these are our two component equations, and we want to calculate the delta H for our target equation, right? First thing you do is say, does it have everything I need, right? There's ammonia here, there's ammonia here. There's nitrogen there, hydrogen here, there's no hydrogen, but there is hydrogen over here. So they're probably going to cancel out. There's oxygen here, oxygen there, water here, water there. Notice that they're all in the wrong place. So we're going to have to do some flipped equations, and we're going to have to use multipliers. Okay. So what I'm saying is, when you're going to use Hess's law, you use your target equation and work backwards and look for those balanced equations with their enthalpies that will satisfy give you the necessary components, either elements or compounds, that will satisfy your added equation. And then do what you have to. Reverse the equations, multiply by a constant. In order to get that final #1 rule, they must add together to your target equation. So here they are. And what we did first was, reverse the two equations, right? Now we have ammonia here on the right-hand side. We have oxygen on the right-hand side. We have water on the left-hand side, nitrogen on the left-hand side, and we have oxygen over here. Oxygen, where is it? No, hydrogen. We have hydrogen over here and hydrogen over here, but the hydrogens don't match. So now we need some multipliers. So what we're going to do is the first one we're going to multiply by 4, right? And the second one we're going to multiply by 3. And this is the result. So now we have this one, and the ratio, the molar ratios of a balanced equation have not changed. They're exactly the same. They're just larger. So if we add these together, what do we get? Well, there's our 2 nitrogens, 6 hydrogens as reactant, 6 hydrogens as product. They cancel. Yep, there they go. And then we have 4 ammonias and 3 oxygens and 6 waters there. So that added together. And what did we do? We used the multipliers to change the values of the enthalpy for our component equations. And we add them together and we find out that this reaction is endothermic to the tune of 1,268 kilojoules. All right, that was one way to get a target equation and the enthalpy for it. The standard enthalpy of formation is another way. But what we need first is to define what we mean by standard enthalpy of formation. This, let me write it down here. This delta H, 0, which is standard conditions of formation, will be a certain value. But you need to know how to write the equation for that value. The standard enthalpy of formation is always for compounds. Elements in their standard states don't have standard formation constants. That's by convention. So what are the conditions? Well, the conditions for pressure are, if appropriate, 1 atmosphere, temperature, 25 degrees C. If you have a concentrated solution of some kind, then the standard molarity is 1 molar. Okay, now that you know the standard conditions, then you need to find out how to write the standard enthalpy of formation. Well, actually, if you have a balanced equation, you don't need to write the equation for this. But it's important that you know how it was derived. How was the standard enthalpy formation produced? Well, let's take an example. Let's say we want the standard enthalpy for water. And under those conditions, water will be a liquid. And you always start with the product. The standard formation, enthalpy of formation for that thing is on the right-hand side. And it's always 1 mole. Once you write it, you can't change it. So all the coefficient work that you're doing has to occur on the product, the reactant side. All right, so how do we make water? Well, we got hydrogen. Standard state is H2 gas. We've got oxygen. Standard state is oxygen gas. Now we need coefficients that will give us 2 hydrogens. It's already there. One of these gives us that. But the oxygen, we only need 1 of them. So this is where you have to use a fraction. 1/2 of that oxygen will do. This is the equation for the standard heat of formation for water. Okay? You can do that with any compound. All right, there's the standard conditions. I'm going to skip this one. I've decided this slide is confusing. So let's go to the next slide. That talks about the previous slide, so we'll skip that one too. All right, so here's the equation. I tried to write it correctly up here. NP products. Yeah, that's right. So if you know the standard enthalpies of formation for your reactants and your products, all you have to do is add up the products times any molar coefficient, right? So the molar coefficient of, well, I don't know. Why don't we go back? Yeah, let's use this one. CH4 plus 2O2 yields CO2 plus H2O. That's 2 of those, 1 of those, 2 of those. Okay. So if we were to use this equation and plug it in here, we would need, for products, we need 1 delta H for carbon dioxide. And we'd need 2 for water. 2 times its value. Then you add them together, and that goes in here. Then you go over here, say reactants. All right. Oxygen doesn't have 1. It's 0 because it's an element in standard state. But we'll have 1 for methane also. So the standard heat of formation for methane is a value, and it's only got a multiplier of 1. So it goes over here. So we take that one, subtract that one, and that gives us a delta H for that reaction. Here's another example. Sodium plus water yields sodium hydroxide plus hydrogen gas. All right. Notice that we've got 2 elements in here, sodium and hydrogen. They don't have a value. They're zeros. So what we need is the product 2 sodium hydroxide. So 2 times minus 470. And then minus 2 times water. 2. And what's water? Water is minus 286. Minus 286. Right? So that will give us our enthalpy for that reaction. And if we do the math, it's minus 368 kilojoules, which is very exothermic. All right. Well, since there's nobody here, I don't have any questions to answer. And whoever's on Zoom, Hasn't stopped me yet, but you're welcome to if you have a question. Okay, let me see how far along are we? We should be getting close to the end. Let's check my slides. Yeah, we're very close. In fact, now I just want to do a general discussion about energy sources. Okay, what are our present sources of energy in this country? Well, there are a few people, and not by any means the majority, who want to get rid of all forms of energy except those they call renewable, like wind power, solar power. There are major problems with those ideas that the proponents, we call them greenies, the proponents of renewables just tend to conveniently ignore. But if we go back in history, we find that for the longest time, our primary source of fuel, of energy, was wood or some type of biomass. It could be wood. Some parts of the world still use dried animal dung. But it was primarily on an industrial scale as wood or wood products. There for a while, wood would go through a process called coking. And they would take the wood and they would heat it up. We call it pyrolyze. They would heat it so hot that it would expel all the hydrogen and oxygen and nitrogen and other elements from the wood fiber materials. And leave behind almost pure carbon. Now, when we coke, we use coal. But wood was it for the longest time. But we started running out of wood. I cut down on the forest. There was a time when the whole Iberian Peninsula, where Spain and Portugal are now, was covered coast to coast with forest. You could walk across the country and never touch the ground on the trees. But it's virtually a barren wasteland now because they cut down all their trees. So we needed a new form of energy. So we went to fossil fuels. What we mean by fossil fuels is a fuel that is stored in the ground. It has been fossilized from something previously, maybe plant life, combination of plant and animal life, whatever the case may be. And we first, at the beginning of the Industrial Revolution, that fuel was coal. It was plentiful. And then we stumbled on other sources like oil, which could be gotten out of the ground much easier than coal. Coal, you have to go down under the ground and dig it out. Well, now we have equipment that will strip the top off and take the coal out in open air. But natural gas is also available as a fossil fuel. Right? Forms of renewable energy. I mentioned wind and solar, but hydroelectric power is also valuable and still used. The problem with hydroelectric is we've used up all of the flowing freshwater sources that can be dammed up and used to convert the potential energy of the flowing water into electricity. Right, so we're kind of stuck there. We can't. There's not much hydroelectric left. The other problem with hydroelectric is when you build a dam on a stream, what happens to the water? Well, here's your stream, the water's coming in, and you build this dam, right? And the water backs up. It's flowing at a certain rate now before you put the dam in. Now you start filling it up, and as the water flows in, it slows down. So this velocity is less, much less than this velocity. Okay, what happens? Well, the first thing that happens is as you slow down, there's suspended particles called sediment. Well, there's sediment once the water slows down, and they settle out and they fill in the basin, right? So eventually, if there's a lot of sediment in the water flowing in, you fill up behind the dam and you got to dredge it out. Okay. So large scale water impoundments are not viable any longer. Nuclear power, right? We talked about nuclear potential energy. Nuclear power can come in two forms, like I said, fission and fusion. All right, if we use fission, which is the standard approach now, because we're still working on fusion. The problem with fission is once you get a reaction started, you have to control it. If you don't control the neutron flux in your reactor, then you get too many neutrons, causing too many atoms to split. You get too much energy, and if you don't have a way of shutting it down or removing that heat, you will eventually have a breach of the containment vessel, and you'll have radiation everywhere. They call that the China syndrome. So fission is, in that respect, difficult to deal with, and is the reason that now the United States hasn't built a new nuclear reactor in probably 40 years at least. There are other forms of fission fuel that are self-controlling, but those technologies are not accepted by the industry or by government. And it doesn't escape me why. It's just, it'd take too long to describe why. But turn to fusion. Fusion reactions only occur under very specific conditions that are matched only inside the core of a star, like our sun. And as long as those conditions are met, the fusion reaction will continue. All you have to do is just stop those conditions, and the reaction shuts down. It's self-controlling. If you have a problem, it automatically just stops reacting. So a fusion reaction, if we can ever commercialize it, would be a great way to solve our energy problem. So, here's my take. If you are ever in a conversation with someone who is adamant about the prospects of, I'm getting ahead of myself, excuse me. This just shows trends of usage, right? So at the present time, fossil fuels are the only way that we can meet the world's needs. And people that are trying to get rid of fossil fuels because they say they cause global warming or climate change or whatever the case may be, are setting the world up for economic doom. All right, so here's what they're saying. These people we call greenies. The Earth's atmosphere is transparent to much of the light that enters, except for some of the ultraviolet light that's absorbed by ozone in the upper atmosphere. That's a different topic. But when the sunlight strikes the Earth's surface, it is re-radiated at a longer wavelength, infrared radiation. So visible light is absorbed and infrared is re-radiated. Now that type of light can be absorbed by some of the molecules in the Earth's atmosphere, which holds the heat in. That's commonly called the greenhouse effect. Now, the greenhouse effect isn't necessarily bad. If we didn't have molecules in our atmosphere that would do that, then the Earth would be just a snowball. We need something to keep the heat in and something to moderate the heat. That's why 70% of the Earth's surface is covered in water, and that's a good thing, because water is, like I said earlier, has a very high heat capacity, and it's very good at moderating the Earth's temperature. Okay, so some of these molecules that they say are being spewed into the atmosphere and causing global warming include carbon dioxide. What they don't tell you is that carbon dioxide can absorb this infrared radiation, and does, but there's only 400 parts per million of carbon dioxide in the Earth's atmosphere. That's a drop in the bucket. There's not enough to cause the temperature changes that they are predicting with their models. And by the way, all of those computer models that they use to predict civilization ending climate change, none of them work. They all fail. What they fail to recognize is that there are other molecules in the atmosphere that are much more plentiful. They may not be as efficient at absorbing infrared, but there's a whole lot more of it. And water vapor in the atmosphere is one of those. What they also don't tell you is that carbon dioxide is plant food. The more carbon dioxide you have in the atmosphere, the more productive plants are. And if we're going to grow more crops, we're going to need more CO2 in the atmosphere to feed the growing population of the Earth. That has been demonstrated in numerous experiments, either in growth chambers, greenhouses, even out in the field. The increase in CO2 increases plant production. Okay, so this is just a schematic showing some of the things that can happen in terms of greenhouse effect. Okay, what are some other upcoming possibilities for energy sources? Coal conversion, gasification. What gasification of coal does is it changes those long chain molecules in coal that contribute to combustion products that are not ideal. And it changes them into virtually methane. And in the process, it doesn't just convert them into methane, it removes the sulfur, it removes any nitrogen compounds, it removes the ash, the uncombustible parts. And you have to put them somewhere, of course, landfills, or some of them work well as soil amendments. But the good thing about that is natural gas is for every joule of energy that you get from methane combustion, you get less carbon dioxide than you would if you were to get the same amount of energy from a mass of coal. Hydrogen. That's the holy grail of chemical fuels. Hydrogen plus oxygen makes water. That's it. It makes nothing else. You could burn it, right? In an internal combustion engine, it probably would work. But if you have a cheap, plentiful supply of energy, like from nuclear, you can split water by a process called electrolysis. And if you have the energy to do it, you can make hydrogen and then take that hydrogen and run it through a fuel cell, which is kind of a battery, but it's a continuous supply of hydrogen and oxygen from the atmosphere. And you can make electricity and run anything off of it. There are certain technological problems with it. Fuel cells run at very high temperature. And then there's the issue of hydrogen. How are you going to store the hydrogen? Because it's extremely reactive. So those are issues that need to be worked out from the technological side. Oil shale. We can get a lot more oil out of the ground by fracking. These resistant types of rock formations respond to fracking and release their oil. They also, in many cases, release gas. And that's why for the longest time, or at least while Donald Trump was president, the US was an energy exporting country, primarily because of fracking. And we were supplying energy to our friends, our allies, and that way they didn't have to buy from our enemies like they have to do now. With the Biden administration, he has virtually shut down all new exploration, development of new or old oil and gas fields. So now we are a net importing nation, and the Biden administration has to go around the world, hat in hand, begging other producers to supply us with energy. Ethanol. Most gasoline that you put in the tank of your car has at least 10% ethanol in it. And there's other issues that make ethanol in your gas bad. But from a purely economic standpoint, the cost of producing a gallon of ethanol exceeds the amount of energy you get out of that gallon when you burn it. So it's a net loss in producing ethanol. In fact, the ethanol industry would not survive if it were not for government subsidies. Methanol is another possibility. If we can convert biomass, in other words, plant matter, right? Just grow fields of plant matter and convert it into something economically, right? You get more out than you put in, then that would be great. Seed oil has been used. In fact, the diesel engine was designed to run on vegetable oil. And it was only till later that we started using petroleum distillates of a certain type to go into our diesel engines. But a diesel engine will run on vegetable oil if you take the right precautions in setting up your engine. Solar, right, has numerous problems. Photovoltaics, what does it cost to build a photovoltaic cell? It pollutes, right? Produces a large pollution stream to build those photovoltaics. And then that's on the front end. On the back end, when they finally lose their effectiveness, in other words, photovoltaic cells don't last forever. Their efficiency gradually decreases over time. And when you have to dispose of them, you got another hazardous materials disposal problem. Wind and photovoltaics both suffer from the problems of intermittent availability. The sun only shines a certain part of the day, and sometimes that's covered in clouds. The wind only blows a certain amount of time. So what you need is a storage mechanism to take that energy that you can get when it's plentiful and store it for later use. Well, that technology is very inefficient. And with this recent hurricane that blew through Florida, I think his name was Ian, what they found out was a lot of the people down there have bought into the electric vehicle craze. They bought electric vehicles with government subsidies, I'm sure. And when the salt water came in and flooded their cars and then receded, their lithium-ion batteries started exploding. So their cars that got wet first, and then after the water receded, they caught fire. So some of these storage technologies are not safe, but there's a lot of research being done on them. And maybe someday we'll be able to store this energy. It's when I think of solar, photovoltaics, and wind, I think of special cases in locations where the sunlight is plentiful or the wind is plentiful, and very limited use, but they're not what they call a base load electricity supply. A base load electricity supply is something like a hydroelectric plant that can turn its electricity on and off like that. Or less flexible are nuclear power plants and coal-fired power plants. They can fire up reasonably quickly and keep the base load supplying. And then the peak load can be matched by other things like gas turbines. That's what gas turbines are used for, peak loads. Like I said before, the economics are uncompetitive. Without government subsidies, these photovoltaics and wind, they would be dead tomorrow. There's not enough demand for them. And I mentioned the environmental hazards. And then there's nuclear. Nuclear solves everything. If you talk to someone who you have identified as a greenie, who's really gung-ho for these renewables, ask them this one question: where do you stand on nuclear power? If they say they're against nuclear power, then they're not for the environment, because nuclear power does nothing to add to the CO2 level. It just has the safety hazard in its history. Nuclear power plants are going up like crazy all over the world except here. And we're finding out that they're extremely safe. There are just rare occasions when something goes wrong. So what you do is you build your nuclear power plants smaller, put them closer to where they're being used. Then if something goes wrong with a small plant, the damage is much less. Okay, that's it for thermochemistry. And let's see, next Friday, I think we have do we have a lab? Yes. Okay, since nobody was here, I don't remember if I handed out waters of constitution and hydration. That's lab number 5. That's the one we will do next on the 14th of October. We'll review for the next exam, plus we'll have that lab. So go to Brightspace, if you don't already have a copy, and get a copy of Waters of Constitution and Hydration, and fill in your lab notebook. If I did give it to you and I've forgotten, then ignore this message. But I will have a look at your notebooks before we do the lab, just to see if you've got everything in order.